Good morning and welcome to Rhythm Engineering's latest webinar, Increasing Motorist Safety Through Next Generation Adaptive Solutions. So as we've discovered through our years of work on adaptive deployments using the InSync ASCT, using advanced signal control technologies to better coordinate signals, to better optimize signals, that can really have a profound impact on motorist safety. So in this presentation, we'll actually take a bit of a historical tour of traffic control and safety and how challenges with traditional signal timing practices led to the development of more automated technologies designed to improve signal responsiveness and overall traffic flows. My name's Jesse Manning. I'm the VP of Business Development for Rhythm Engineering. And many of you know me. For the last several years, I've been pretty steeped in adaptive technology in the traffic industry, but I've actually got a degree in history. So the evolution of traffic control as a means of adapting our cities and our roadways to the new reality of early 20th century transportation, it's particularly fascinating to me. You know, city streets before the advent of the motor vehicle were places for pedestrians, places for horse-drawn carts and vendors selling their wares. Really, the development of the car and its subsequent popularity with and its adoption by the public was not some carefully controlled government project. One day, streets were meant for walking, and the next, people on foot had to compete with heavy vehicles traveling at speeds that were higher than any seen before, and these cars were driven by inexperienced owners. So driving went from initially this leisure activity to a part of everyday life. It is so much a part of everyday life that most of us not only rely on our cars for our daily commutes, but driving is such a part of our lives that most of us can't even remember details of those daily commutes. So vehicles continued to develop as a necessary means of public transportation and freight. An entire industry that was devoted to safety arose around these vehicles. Think about it. Basic rules and regulations that are second nature to us today, like driving on the right side of the road, those actually had to be developed and standardized at some point. All of our norms, like directionality, intersection behavior, signage, speed limits, those were all developed in response to the presence of motor vehicles. So the first car didn't pull onto a road that was ready-made for it. Cities and counties and states across the nation, they had to play catch-up. Even the pedestrians that once ruled city streets had to adapt to this new reality. So the first crosswalk and the associated laws that were put into place around that was found in Kansas City in 1914. And by the 1920s, the automotive industry had begun this massive public relations campaign designed to displace the pedestrian for good. Jaywalking became not just a commonly used term, but also the law of the land in many metropolitan areas. Here's where the term came from. 100 years ago, jay was a term that was synonymous with stupid. So jaywalking basically meant stupid walking. And jaywalking became mocked by the entire automotive industry. They had this massive public relations campaign, and over the course of the 1920s, regulations against the practice were picked up by governments all across the nation. So with cars ruling the roads, it was really no longer safe to be a jaywalker. One common theme that we return to over and over again with motor vehicle-related devices and vehicle-related regulations is safety. So again, this entire industry devoted to safety arose out of the appearance of automobiles. Speed limits were put in place to keep drivers from careening along dangerous roads or driving through city streets at unsafe speeds. Standards like driving on the right were to prevent collisions. And eventually, police and municipal engineers saw a need for enhanced control systems at intersections in metropolitan areas. The first electric traffic signal in the United States was developed by Lester Wire in 1912. So Lester Wire was in charge of the municipal traffic force in Salt Lake City. And his concern wasn't necessarily intersection safety, but it was his officers. He was concerned that those traffic control officers that were required to stand out in the middle of the intersection and direct traffic, that they were dealing with busier and busier intersections. More people were driving, the traffic volumes were getting heavier, and those guys had to stand out in all sorts of weather. So his invention, which was a birdhouse-looking traffic signal, it gave basic green and red indications to opposing flows of traffic to control access through city intersections. So initially, when the first traffic signal was put in place in Salt Lake City, pedestrians actually made fun of motorists for following these automated directions. The public did not immediately warm up to the idea of an electric traffic light. However, Wyer's invention was a hit with the police force. So you saw variations of this electric traffic signal start to crop up all over the United States and Canada over the next decade. Among the most famous variation, many of you know about this, Garrett Morgan's 1923 patent, and it was more reliant on semaphores and text-based directions than the electric light combination that we know and love today. However, his patent was really important because it was snatched up by General Electric. They bought it for $40,000. What that led to was increased standardization among electric traffic lights and mechanisms over the following decades. So traffic signals have played this huge role in increasing intersection safety, particularly in urban areas. And while they played that role, engineers began to develop new devices to offer more nuanced control of signal timing. So for safety purposes, it's unwise to waste green time on unused side streets while there's heavy demand on the main line. So the electromechanical controller looks very similar to a sprinkler system timer, Christmas light timer, those basic mechanical timers that we know of today that we use in some of our household devices. The electromechanical controller was able to allow timing engineers to more easily control signal timing based on the actual traffic patterns at an intersection or along an entire arterial. So by placing pins along a dial at specific intervals, signal timing could be more easily modified to better suit the general traffic pattern by time of day. Many of today's common terms, splits, dials, cycles, offsets, those all come from the physical characteristics of the electromechanical controller. Those very same characteristics were replicated in the new age of digital controllers that began in 1976 with the NEMA TS1 standard. And again, safety was a driving factor in the standardization offered by the NEMA TS1. It was basically the functionality of the electromechanical controller in a digital box, and it was designed with universality in mind, designed to spread standards across regions. This advancement was followed by the TS2, the TS2 Type 2, and the 170 and 2070 world that was pioneered by the New York State DOT and Caltrans. All of these boxes were designed for easier access, faster programming, and more granular control of options at the intersections. Those were all hallmarks of these units, and all were governed by the NEMA ring and barrier structure. That was at the core of their programming. So whether it was the static operation of the old electromechanical controllers or the new flexibility offered by more standardized and computerized operation, controllers improved intersection safety. It was a way to better time signals based on the actual traffic patterns that had been observed at intersections and along arterials. So it improved safety, period. And when talented engineers applied their signal timing prowess, even the old electromechanical units could be timed in such a way to offer excellent mainline progression through a series of signalized intersections. So offsets were scheduled in such a way that common cycle lengths on controllers across an entire network of intersections could facilitate progression from one intersection to the next. So on this diagram, you can see that the reference points match up, and our mainline directions are served in such a way that both cars here, both eastbound and westbound, progress through the network of 3 intersections with no stops. This analog mechanical progression, it forms the basis for even modern signal timing practices on the most modern of controllers. However, those standards are not without limitations. So while this particular diagram worked, if we throw a 4th intersection onto the corridor, this time with a distance different than those between the first 3 intersections, bidirectional progression starts to take a hit. So our eastbound car will be able to progress through without an issue because the reference points line up really nicely for the eastbound direction. But our westbound car suffers a stop at every single intersection. That's just the limitation of the analog nature of a ring-based structure. We had to force stops along one direction in order to favor the other. So we forced stops for the westbound in order to progress towards the east. And this is a sacrifice that many traffic engineers know they have to make. One direction of travel sacrificed in favor of the other. And it's a reality that our motorists deal with every day. Even the best signal timing practices can't overcome the limitations of an analog system, or even systems that emulate that analog operation. That can lead to congestion and start and stop traffic for many motorists. A lack of coordination, of course, that leads to motorist frustration. Frequent stops can actually lead to distracted driving. And even moderate improvements to signal timings, those have been proven to increase safety. But when we're working within the confines of an analog system, and we're forcing stops due to the limitations of that equipment and the increasingly complex math problems of bidirectional progression, we're actually inviting distracted driving and the accidents that come with start and stop traffic. So unfortunately, the very technology that we've developed over the decades forces limitations on us that have introduced new safety hazards that really weren't even considered during the advent of electromechanical controller technology. When the first engineer designed an electromechanical signal controller, he wasn't thinking about people who were stopped at red lights playing on their smartphones. If a signal doesn't have the means to adjust to changing volumes, motorist frustration and safety hazards are just going to increase. So while all of our modern advances in traffic control devices have actually made life easier in a lot of ways, they have introduced new challenges and new limitations in others. It almost makes us long for the very first adaptive traffic control system, almost. Well, I'm calling this adaptive traffic control, a traffic tower in the middle of the intersection. This is an image from Detroit in the 1920s. A busy intersection didn't have a traffic signal, but it had a traffic tower, and it was manned by a traffic control officer. Now, the beauty of this traffic control officer in this particular setup was he wasn't locked into any pre-programmed script or cyclic order of movements. He was able to serve traffic in a flexible, fluid, dynamic way based on the priority that he saw in real time. That desire for even more granular control in response to varying traffic volumes and intersection demands actually drove the development of adaptive signal control technology, which has existed in various forms as far back as the 1970s. So to understand the safety benefits of these technologies and how they improve upon the traditional timing practices that we all are used to, I'm going to call on the generational definitions written by the planning and traffic engineering experts from Urban Systems Associates in San Diego. They have generationalized adaptive systems, and the first generation of adaptive control, and I say adaptive in quotes because it's a little bit of a stretch for the term, the first generation of adaptive would be similar to the ATSAC system, pioneered by the city of Los Angeles in the early 1980s. It was a remote control and monitoring system, and it was followed up by more automated forms of control in the second generation of adaptive systems. We're now looking at a third generation of adaptive technology, transitioning to a distributed architecture that's going to move further away from the constraints of traditional controller technology. So we've established that traditional controller technology has its limitations. And with those limitations do come some particular safety concerns. Frustrated motorists, distracted driving, start and stop traffic. There are, of course, other benefits of automated adjustments and adaptive signal timing. So when we base that on volume and delay, before and after studies have shown that adaptive systems can reduce overall system delay, we can achieve better progression through a network, we can reduce queuing, we can stave off the onset of congestion, and we can actually reduce fuel use and emissions. Many agencies around the country are able to apply for grant funding because all of these benefits, reduction in delay, reduction in the number of stops, improvement in progression through a corridor, they also have those peripheral benefits of reducing fuel use and reducing emissions. So they can apply for grant funding that is focused on air quality. But the safety benefits of a better functioning signal system cannot be overstated. Let me take you on a walk through the different generations of adaptive technology. Safety, again, was a primary driver when the ATSAC system was pioneered in Los Angeles before the 1984 Olympics. While the system allowed engineers in their high-tech TMC the ability to remotely monitor and manage the traffic volumes and signal status of intersections throughout the city, the Los Angeles team was actually ready for a variety of different scenarios meant to not only move traffic better, but to keep motorists safe. So prior to the '84 Olympics, one of the early simulations that they ran was a what-if scenario of what if a helicopter crashed on a major freeway? How would the engineers react? How would they change the signal timings? How would they reroute traffic and retime the signals to deal with the inevitable panic around such an event? It was actually not long after that system went live, there actually was a helicopter crash for real. The engineers were prepared. They were able to move traffic quickly away from the incident, and undoubtedly they kept Los Angeles motorists safe by being prepared for that. But there was a very manual component to the ATSAC system. This allowed remote insights, a lot of data being collected, signal status, timing plans could be viewed. However, you needed a team of engineers to be able to remote into those signals and actually make changes based on the needs of the intersections or the arterials. So the ATSAC system gave engineers insight into signal status in ways that were previously unheard of. And with a high-tech communications network and powerful software for the time, those manning the TMC were able to make rapid changes if necessary. Like I said, this first generation system was very, very manual. It required a team to monitor and react to those issues as they arose, and while a first generation methodology was cutting edge over 30 years ago, it seems pretty archaic by today's standards. Not to mention, it's an impossibility for most agencies. Cities, counties, even state DOTs are dealing with continual reductions in staffing levels. So the idea of having a team of engineers ready and waiting to respond to incoming data and reports, it seems like a product of a bygone era. Interestingly enough, we're actually starting to see a resurgence of first-generation thinking with the advent of high-resolution data that provides really even more incredible insights into intersection and corridor performance. So those of us here at Rhythm are absolute believers in the power of good data. However, both second and third generation adaptive technologies have been developed to automate the use of this data and subsequent adjustments to signal timing. Modern controllers or peripheral devices or ATMS platforms, they are starting to give agencies incredibly detailed data sets, but they're unfortunately being advertised right now as complete solutions. Dr. Ayrton Coles from the Center of Transportation Research, he recently presented at an Advanced Traffic Technology Symposium in Knoxville. And during his presentation, while he covered ATSPM, he made it absolutely clear that while high-resolution automated traffic signal performance measures will give engineers levels of detail that can help them fine-tune their systems and identify problems with levels of service, collecting data alone is just a half measure. You actually need to be able to do something with the data. So second and third generation adaptive systems exist for that purpose, taking in data and actually doing something proactive with it, leading to exponentially faster adjustments that propagate safety improvements throughout impacted corridors. So the development of second generation adaptive systems came from automating the manual components of first generation systems. In other words, taking much of that human component out and turning over signal timing adjustments to a central server operation. These developments first appeared in responsive systems that remotely implemented new timing plans in response to changing patterns. The example shown here would, for instance, after the first cycle, change to a plan that serves westbound movements first after the mainline service, completely altering the timing plan moving forward based on collected data and calculated responses. Adaptive systems, and this is where we move into the second generation of adaptive, as opposed to simple responsive systems, it allowed central server operations to evaluate changing volumes to create more nuanced adjustments to the needs at the intersection. So in this example, the system, through data collection and evaluation via deployed detection devices, let's say it determines that there was more volume on the eastbound movements than the timing plan and its maximum green times for those splits was able to serve. In other words, the movements suffered from split failure. So the system would collect all that data, send it back to a central server which would analyze the split failure, and it would determine that if the eastbound movements were able to take a little time from the westbound movements during the next cycle, the adjustment would be appropriate to serve that volume of traffic. This slight adjustment is made in the next cycle based on the system's evaluation and recommendation. So second generation systems have obvious benefits: automated responses and nuanced adjustments to changing traffic volumes through dynamic splits, dynamic cycles, and dynamic offsets. Many DOTs consider this to be the very definition of adaptive. And while those adjustments allowed systems to better cope with variable traffic demand, they suffer from some operational drawbacks as well. I've been doing a lot of traveling in Canada over the past year, and nearly every agency I've met with has said the same thing. We know all about adaptive. We tried it 15 years ago and it just didn't work for us. The system was too hard to maintain, the performance just wasn't what we were looking for, and we could not afford all the detection that was required to truly optimize the results. So their experiences are actually fairly common. To truly get the best out of a second generation adaptive system, you may need to deploy really extensive detection. At the very least, you need stop bar and advanced detection so as to better estimate cues. Even with very extensive detection deployed, and that extensive detection may be not only stop bar and advanced, but upstream detectors or downstream to be able to pass information in a peer-to-peer way to the next intersection. Even with all that detection deployed, you can see on our map the limitations of single point detectors. So each detector in a second generation system feeds the system with ones and zeros. It's basically just presence data. But take a look at the north side of this intersection. You can see that we've got cars coming out of the mid-block, but they're not triggering the advanced detection. They're too far downstream to trigger the upstream detection. Missing that advanced detection, the first time this intersection would ever see that new volume influx would be at the stop bar. So by the time the intersection had called into the central server, relayed its data, and requested analysis and adjustment, it's too late. The pattern's changed again, and the affected movement may not have the same volume or priority that it did in the previous cycle. So second generation systems still use controllers as the basis for all timings. You'll recall the limitations of the electromechanical and the analog controllers. That means that they still suffer from the same analog limitations even in second generation adaptive systems. So despite the improvements in analytics, improvements in adaptive algorithms, and adjustments to varying traffic patterns, these systems actually managed to hurt the adaptive name more than help when they struggled to gain traction in the early 2000s. So what's the difference with a so-called third generation system? Well, for one, they do away with the need for extensive single point detection. A third generation system feeds a separate computer processor at the intersection, not the controller, a separate processor. It feeds it with estimated cue data so as to better analyze the totality of each approach and phase, not just single points of data that may or may not be triggered. So as we introduce some cars onto the scene, we can see that live cue detection picks up their presence all throughout the approach, not just at single detector points. That's going to allow the system to better analyze cues as well as the delays on stopped movements, all of which can be factored into the algorithm. That cue analysis greatly reduces the amount of gray area at each intersection, which gives third generation systems the ability to respond much more appropriately to actual intersection demand. Furthermore, the changes that take place are happening at a local level. The distributed architecture doesn't need to call back to a central server for instructions, but it can make the instructions, the changes to the intersection on the fly. Mid-cycle, even mid-sequence adjustments based on variations in volume, real-time traffic demand. So those second generation systems, and I don't want to overlook the benefits of a second generation adaptive system. They are tremendous improvements over the manual operations of first generation systems. They're able to make these nuanced changes based on collected data and then instructions that are sent back to the intersection. Timing plans are adjusted, but pre-planned sequencing largely remains the same. The only things in a third generation system that are pre-planned are really the global constraints, your mainline movements that facilitate progression through the corridor. So outside of those pre-planned movements, which can begin early, they can extend, they can truncate according to real-time volumes, each cycle's phasing and sequencing may be totally different based on the actual present demand at the intersection. So this has finally started to break with a long-established NEMA ring-based structure that locks in sequences for extended periods of the day. That NEMA ring-based structure is limited in its ability to adjust, even with the most powerful adaptive algorithms. So moving from a second-generation mentality to a third-generation mentality, that really allows us to break out of that structure and serve traffic better based on real-time priority. So what does this mean for safety? Let's get back to the topic at hand. Adaptive systems, and in particular the powerful flexibility of third-generation adaptive, it obviously can increase efficiency. But outside of mainline progression, how exactly can signal service that seems to violate the expected norms actually increase safety? Well, first of all, let's acknowledge that better mainline progression absolutely increases safety. When a motorist can make it all the way from point A to point Z with few stops, the smooth progression through a network cuts down significantly on rear-end collisions caused by start and stop traffic. A third-generation system, though, has the ability to serve phases in non-standard orders, essentially jumping back and forth across the barrier to serve demand as necessary or better facilitate bidirectional progression. So when both mainline movements are flowing smoothly, safety increases above and beyond what can be achieved under normal, traditional architectures. Also, when third-generation adaptive is serving phases dynamically based on priority, the service may not be as predictable, and every phase technically may be reserved within the cycle length. Those of us at Rhythm always get the question, well, doesn't this violate motorist expectation and increase the amount of complaints? So the answer to that is, it depends. We've certainly worked with agencies where the motorists have been surprised by the activation of the adaptive system, and for a short period of time, because the signal timings are different, complaint calls increased. On the other hand, those agencies that do engage in a PR campaign to both alert motorists of upcoming signal timing changes and educate the public on how third-generation adaptive control works and why it's beneficial, we actually see a much more enthusiastic adoption of the new system by the public. Either way, once the public is used to how the system operates, dynamically, safely, based on real-time priority, we've not only seen motorists become more attentive, but we've seen safety increase across the board. And those aren't Rhythm's numbers. In 2015, the Virginia Department of Transportation released a comprehensive study of 13 in-sync adaptive corridors, a total of 151 intersections. The standard measures of effectiveness were studied, of course, and many of the corridors showed improvements like those shown here from Charlottesville. A decrease in mainline stops, increase in average speed, a decrease in travel time, overall system delays, which included side streets, those were reduced as well. But the most striking and by far the most important metric from the VDOT study was the 17% reduction in accidents. And that was a consideration from all installed systems. The VDOT study is wonderfully detailed, and it's this very full and complete evaluation of exactly why and how third-generation adaptive systems can create safer corridors. With improved mainline movements and enhanced bidirectional progression, the study showed that the expected decrease in rear-end collisions actually happened, and we do expect that. Even with moderate improvements to signal timing, if you're moving your main line better, you're cutting down on those rear-end collisions. Smoother traffic, fewer starts and stops, better safety. but we also saw a decrease in angle collisions on VDOT's study corridors. There's more qualitative evidence than quantitative with regard to non-sequence-based adaptive operations, but our historical observations have shown that as motorists adjust to the way the adaptive system works, dynamically, based on priority, not a pre-programmed order, they actually start to pay more attention at the intersection. They take advantage of resurfacing as it's offered. They are far more attentive when they're stopped at a red light. And that's a goal for all of us, increasing the amount of attention motorists pay to the driving task. So when phase orders can't necessarily be predicted, as they can on so many morning and evening commutes, motorists actually develop a tendency to put down their phones, to pay attention to their surroundings, even when stopped at a red in heavy traffic. The InSync system, which is a true third-generation distributed architecture, real-time adaptive system, has had other safety numbers reported from deployments throughout the Midwest and South. And while these numbers don't have the long-term backing and quantitative analysis performed by VDOT, they do corroborate how better traffic flows and priority based on intersection service can actually decrease accidents. So these are based on police reports from before and after installations, where the city of Topeka saw accidents fall by up to 27% on adaptive corridors. Lee's Summit in Missouri saw a 17% reduction in crashes, and they actually ended their red light camera program because the drastically improved mainline progression nearly eliminated red light running altogether. Springdale, Arkansas reported a 30% decrease in accidents on their central adaptive corridor, and Evans, Georgia experienced decreases in accidents up to 26%. In addition to the various third-generation benefits that take efficiency to the next level, InSync is the only adaptive system which, with these kind of thoroughly researched and agency-backed safety numbers. So that same third-generation algorithm, it's been optimized and taken into consideration for other road users as well, for pedestrians, cyclists, even public transportation. The best example I have is in Kansas City, where the InSync system was installed on a 2.2-mile, 21 intersection route where the city's streetcar operates. The streetcar was installed about a year ago, began running about a year ago. This is in an urban downtown core. So we can expect heavy pedestrian traffic, and you've got your transit traffic, not only with the streetcar, but with buses as well. So we started utilizing pedestrian detection. That way we could eliminate recall. And Rhythm has been able to work with the city to reduce travel times for motorists due to that pedestrian detection and better ability to coordinate along main lines for motorists. We've been able to reduce their travel times by up to 25%. We're still able to guarantee that same quick and efficient pedestrian service. And we also keep the streetcar running at its guaranteed service levels through a dynamic transit signal priority system. So we've seen how third-generation adaptive systems provide dynamic service and overall results above and beyond what traditional signal timing practices can provide. And that third generation even goes far above first generation and second generation adaptive systems. Those dynamic operations are proven to produce safety. There's the numbers out there to back it up. So, why the hesitation to implement? Sometimes it does come down to that question about motorist expectation. In fact, some second-generation system vendors are really proud of the relatively static service their systems provide, claiming that dynamic sequencing can actually cause safety issues. But the data simply disagrees with this. Motorist safety is improved when the dynamic of intersection service is changed. There's a difference between motorist anticipation and motorist expectation. So when traffic engineers cite motorist expectation as a reason to not change their timing practices, they are thinking usually that predictable intersection service improves the safety of their drivers. It's what people are used to. But guess what? The motorists aren't expecting predictable service. They're expecting efficient service. They may be anticipating a certain sequence. They may be anticipating a pre-programmed cycle. But that anticipation leads to motorist laziness. Distracted drivers that are simply going through the motions of their day-to-day commute without paying attention, without thinking. That's why we believe that third generation adaptive operations not only give motorists what they ultimately expect, which is efficient service, but we absolutely know it increases safety. Dynamic sequencing, dynamic phasing, those truly dynamic operations, even though it seems somewhat counterintuitive to the technology that we've relied on for decades, it increases safety, and the numbers back that up. And that's how you today can capitalize on 100 years worth of developments in traffic technology by moving towards third generation bridge building systems that are going to take us to the next level of efficiency and safety. Folks, we've come to the end of our presentation. I want to thank everybody for their time, and I hope this was not only educational with regard to the types of adaptive technologies available, but also in showing how safety is a core, proven benefit of third generation deployments. At this time, I'd like to open it up for some questions and possibly additional discussion points. If you have questions, please type them into the chat area of GoToWebinar, and we'll take questions in the order that they're received, and we'll go ahead and begin the second half of our webinar now.